Hello everyone, welcome to our next episode of Conversations about the Cosmos. My name is Samuelovo. As always, Norbi is here with me.
Hi.
And we have very special guest, Kip Thorne. Welcome.
Pleasure to be with you.
So, summer is coming and you are very busy. But when you have a free afternoon, maybe, I don't know, you'll be spending the night under the clear sky and you look up, what are you thinking about?
I just take great pleasure in the beauty of the stars. It needs to be clear in a very dark sky. And I grew up with that in the Rocky Mountains in the United States with a clear, dark sky. And it was so just inspirational, even to the point of being emotionally inspirational. So it can cause me to think a little bit about what's out there, but more than that, it really is just the pleasure of being surrounded by nature in this way.
When I thought about it, I noticed that, well, the night sky was the first thing in human history that made sense. There were some patterns, something appeared every week and so on. So then we thought it makes sense. And now after basically centuries of understanding the universe, I think we are completely back to the beginning and it's completely mysterious. So do you think we'll understand completely the universe at some point, or it will be mystery forever?
I don't know. You can ask the same question about the laws of physics that control the universe. As we go deeper and deeper, we find the laws of physics change. So we go from a classical world to a quantum world. And there seem to be nested layers of structure in the laws of physics. And whether that continues on and on forever or not, I don't know. There's a lot of speculation about that, but I prefer to just move forward and we'll find out someday, or maybe we won't because it will be nested and we'll keep going.
Do you think the feeling you had when looking at the sky makes the difference between the motivation of physicists and mathematicians? Because we are trying to understand how the world works, but I think in our case it's more personal, or how to put it?
Yeah, I think a physicist certainly is pushing to understand how the world works. A mathematician is pushing usually to understand mathematical structures. But because the laws of physics are written in the language of mathematics, mathematics is crucial to me as a physicist. And it is that plus observation and experiment are the things that tell us what's really going on out there. And as I have grown older and wiser, I think I have come to appreciate the importance of the mathematics more and more. That, for example, it was crucial for the work that I was doing that we be able to understand what happens when black holes collide. And we could only understand this by solving equations that Albert Einstein gave us on a computer. But those equations, for several decades, when the best experts were trying to solve those equations on a computer, the calculations kept blowing up. And it turned out the problem was that the people that were doing this, which were close colleagues of mine, and I was involved peripherally, did not understand the full mathematical structure of Einstein's equations. And they were missing some very, very deep mathematics. And that really taught me the importance of fully understanding the mathematics, at least under some circumstances. There are other circumstances where physical intuition with a relatively small amount of mathematics can enable you to make some rapid progress. But in the end, you really have to have rigorous mathematics to understand with certainty what the laws of physics are saying.
Is this a real certainty? Because, well, mathematics boil down to axioms. And we know that the fifth axiom of Euclid was problematic, and now there is the axiom of choice and so on. So you can really be sure that the proof you got is the correct one, but was the starting point the correct one?
So,
I'm not so sure, even with mathematics.
Well, yeah, yes, yes, but the thing that tells us whether we've got the right starting point, to a great extent, the key thing is the observations, the experiments. And so for a physicist, going back and forth between the mathematics and the experiments, the mathematics and the observations, is crucial for ultimately getting to the ultimate truth. So if we were dealing with mathematics by itself, then yes, there are issues of undecidability and so forth in the mathematics that are very interesting issues. But I'm not nearly as deep as some theoretical physicists are in mathematics, but I have not seen a place where that became an issue in physics. The bigger issue is tying the mathematics to experiment and observation.
So tying the experiment to observation, tying the theory to observation. So you were working on predicting the result of black hole mergers. In the 1970s, did you believe that in your lifetime the gravitational waves from black hole mergers will be detected, that you will see those observations?
At first I was skeptical. Joseph Weber, a good friend of mine, invented a technique for searching for gravitational waves and thought he saw them in 1969. Other experimenters following his techniques didn't see them, and it became clear that they were not there in his detectors. Ray Weiss, a close friend of mine at MIT, invented an alternative technique, which is the one that we ultimately used and had success with in 1972. This technique involved using laser beams to monitor the position, the separations between mirrors. And when a gravitational wave came by, it would stretch and squeeze space between the mirrors, and so they would appear to get closer and farther apart. And a technique called laser interferometry that he conceived and then began to develop in his lab, and others began to develop, for example, Billings Group at the Max Planck Institute for Physics began in Munich. This technique, when I made careful estimates of how strong the waves would be, it seemed clear to me that you would have to monitor the motion of a mirror to a precision 10 million times smaller than the individual atoms of which the mirror is made. And that was fairly clear to me in 1972 when I learned of Ray Weiss's idea. And it seemed to me that that was crazy. That Weiss, Ray, whom I had known at Princeton when I was a graduate student, he was a postdoc, that something had gone wrong with him. How could he really think he could do this? And I was totally skeptical for about 3 years. But then I had extended discussions with him, extended discussions with Vladimir Braginsky, a superb experimenter in Moscow. And I did calculations of my own, analyzing his ideas, Weiss's ideas. And I came to agree that there was a possibility of success. So by 1976, I thought there was a high enough possibility of success that it would be worthwhile for me to devote much of my career and that of my students to trying to make this happen. So I would say I didn't put a probability on it, but certainly I was thinking that this was more likely than not that the success would come.
So by 1976 you were convinced?
I was convinced enough to propose to Caltech, to my colleagues at Caltech, that we should start an experimental group in parallel with Ray Weiss's group working on this. And so Martin Schmidt, who was the chair of physics, math, and astronomy at the time, he was the man who discovered quasars. a few years earlier. Martin appointed a committee to look at this. And I was on the committee, and we, as was Barrym Barishem, who ultimately became the leader of our LIGO project decades later. And this committee looked at it in depth for a period of about a year and came out with a report saying that this really was worth doing and worth Caltech getting involved in. At the time at MIT, Ray could not get anybody interested in this. But at Caltech, there was enthusiasm generated, and experimenter was identified to bring to Caltech to initiate our project, Ronald Drever, who was coming from Glasgow, Scotland. And Caltech put about $2 million of its own money, which now is equivalent to about 12 million euro, to get this project started. That was a lot of money, private money, and that was enough to make people at other institutions start paying attention. And that's how we got started. But we got started through this in-depth study by people who were experts in relevant technologies, and who, after a year of study, came to agree with me that.
So basically, from the first idea, when you got convinced that let's devote my time to this, to the first detection, it took almost 40 years.
Almost 40 years, and it was 50 years from the time when I began looking at ways to detect gravitational waves and studying them theoretically. And 50 years from when Rayem Weissem also began.
So, in the Czech Republic, we are developing a mission called QVIC, which is the main objective of which is to look at the sources of gravitational waves in the UV band. What would be the most exciting observation in your mind that the satellite could do?
Well, I want to see the UV radiation coming from a black hole tearing a neutron star apart.
Black hole neutron star merger, yes.
So, and the neutron star is about the same size as the black hole, roughly, and we can see the gravitational waves. We know when the star starts to get torn apart. We can see the beginning of the star being torn apart with our gravitational wave detectors. And if you can see the UV radiation produced when it gets torn apart, and when the very hot interior of the neutron star is exposed to the external universe, this will be a wonderful thing. And is likely to be a set of observations that those together also with X-rays and gamma rays and optical and infrared and hopefully even neutrinos.
So probe of the properties of matter under the ultimately extreme conditions.
Right. So it'll be a powerful way to probe the properties of matter under extreme conditions and to probe the properties of neutron stars. You know? So that would be my biggest hope.
So let's hope this will be achieved.
Yes.
One of your first major results was the collapse or not collapse of magnetic fields, and that led to your famous hoop conjecture. And you describe the process like you got the problem to solve and then spent months just playing with equations and so on. But what is your first thing to do when tackling a new difficult problem? Do you just some dimensional analysis or simplify equation, or how do you tackle difficult problems?
Well, I think the first thing I do is try to use my physical intuition to make guesses as to what's going to happen, because those guesses are crucial to being wise about what you calculate, or wise about what kind of instrument you try to design. For me, physical intuition is based on mental pictures, mental diagrams. So in some sense, I carry around the laws of physics in my head, expressed in terms of mental pictures. And I use those then to guide my choices as to what direction to go in either calculations or experimental design.
How do you build this kind of intuition? Solve 200 different problems from general relativity and then you can...
In some sense, I started this when I was a student. I went to Caltech as an undergraduate, the same place as I have had essentially all of my career. And when I arrived there, I discovered that my mind worked a lot more slowly than the other students' minds did. And so I had to have a strategy so that when I learned something, I learned it better, and I wouldn't have to relearn it. And the strategy I developed was I kept notebooks in which I would write down and draw pictures that explained to me myself the most important things I was learning about physics, and then explanations as to why this was right, mathematical derivations or drawings, and so these notebooks with lots of drawings in them and with also a lot of calculations, sketches of calculations, became, in some sense, my memory. The memory would be built. It would truly become part of my memory if I had done that. But I could always go back to those notebooks to refresh things. So that played a big role in how I build up physical intuition. I was not consciously trying to build physical intuition this way, but I think it played a significant role in it. But I think another aspect of this is that everybody's mind just naturally works in some particular way. Some people think in terms of pictures, other people think in terms of geometry. Some people have no sense of geometry, no sense of direction. I have an intense sense of direction. I can tell you every decade since 1900 is a line that points in a particular direction. And so we go from 1900 to 1910 to 1920 to 1930. But it's a kind of a complicated pattern, but time is laid out for me in this strange geometrical way. And that's not the case for, I suppose, for most people. And so because that's how my mind works, and has as long as I can remember, that's part of the foundation for my particular way of doing physical intuition.
Before I let Norbi ask his question, I have a different one related to mentoring and learning and so on. You were sort of a lone wolf, like prefer to do your calculations alone, but you also both had great mentor and supervisor, and supervised many great physicists. So how to balance those two? Prefer to work alone, but also being part of a huge collaboration?
Well, so working with my individual students, with my research group, is more like working alone. It's very different from working in this gravitational wave project where there are 1,000 people. In the end, when we first saw gravitational waves, we had 1,000 members of the collaboration in 15 nations in something like 80 different institutions. That's one way of doing science, which I don't like, but we had to have that in order to have success. But working with a small group of several PhD students and several postdocs, I'm happy with that. I'm also very happy to go off by myself. But I met Robert Oppenheimer in the later years of his life when he was the director of the Institute for Advanced Study and in Princeton, and I was a graduate student. And I was really impressed by him, by his quickness of mind, his ability to see things that other people didn't see, just in conversation or in seminars. And I started learning more about him. He had been a professor jointly at Caltech and at Berkeley, University of California at Berkeley in the 1930s. And all of this history comes through in the movie Oppenheimer that came out a year ago. He had a particular way of working with students, and I learned about that because I knew his students. They were colleagues of mine. I patterned my own research group after that, a research group where we would have group meetings every week. Sometimes the group meetings would go on as much as 6 hours. Sometimes they'd only be 1 or 2 hours. But I would go around and have each student or postdoc in the group describe what they were working on, what progress they had made in the preceding week, so that everybody was aware of what everybody else was doing, and so that they could comment on each other's work as well, and they could be stimulated to collaborate with each other just through these group meetings. Basically create an atmosphere in which there are many ideas floating around and many opportunities then to explore ideas that the students were exposed to. An atmosphere where every week we would have 1 or 2 visitors, and those visitors would similarly share what they were working on and would comment on our group's work. So that was a mode that's not so much a lone wolf mode, but it's a small science mode that I really enjoyed. And I really also enjoyed going off by myself for days at a time and struggling with a research problem. What I did not enjoy was being in a collaboration with 1,000 people. But that's what we had to build in order to have success.
Both modes of work are necessary.
Yes, both modes of work are necessary. But once I had trained enough young people working in this project that they could take over the roles that I'd been playing, I happily pulled back from day-to-day involvement in
the first one is project. Much more enjoyable.
Yes.
So you are one, to my understanding, you are one of the few Western researchers who actually, during the Cold War, went to the Soviet Union and also developed working relations with the Soviet relativistic astrophysicists. Yeah. What were the main differences, similarities, how they were working and how you were working?
I think there is a huge amount of commonality. So I did this because in the areas I was working in, it was obvious that the greatest work, the most brilliant people working, were in Moscow, in Cambridge, England, and at several centers in the United States. And I wanted the benefit of being able to interact with the people in Moscow. This was, it was Yakov Borisovich Zeldovich, who had been one, with Andrei Sakharov, was one of the 2 fathers of the Russian hydrogen bomb. My PhD thesis advisor, John Wheeler, had been one of the key contributors to the American hydrogen bomb. So a very strange thing. Mm. I was the next generation, and all that nuclear weapons work was behind us. But both Wheeler and Zeldovich and Sakharov had moved into astrophysics afterwards because there's such exciting things to do, challenges. And the huge commonality in how you do science, I mean, between the 2 cultures. The big differences were just from individual to individual. And Zeldovich, whom I regard as nearly as much of a mentor for me as John Wheeler was, Zeldovich had this amazing ability to take a area of astrophysics, an issue in astrophysics, such as the X-rays emitted by gas that's flowing around a black hole. Take an area of astrophysics and boil it down to some very simple model from which you could get the essential features out, and use it to scope out very quickly what may be going on. And his skill at this was something that's unmatched by anyone else that I knew. He had physical insights that other people hadn't had. He and Richard Feynman were the two colleagues of mine that I think were most insightful at seeing new things. And so I wouldn't say that there was much difference in...
It's more commonalities.
There was more commonalities, and the issue is they had several absolutely superb physicists. The cross-fertilization that resulted from my being able to interact with them and come back and tell colleagues in the West what was going on there, and basically feed information and points of view back and forth, that played a significant role in the development of the fields I was working in.
So currently the situation is maybe in some ways even worse between the West and
it's far worse.
And Russia.
Very different.
And there are the opinions that even scientifically we should stop working together with the Russians. For example, the eRosita satellite, the eRosita instrument on the spectrum Röntgen gamma satellite has been switched off because after Russia attacked Ukraine, or with China, Americans working for NASA are actually by law not allowed to interact with their Chinese colleagues. What do you think? Should we continue collaborating scientifically regardless of...
So I'm not sure. Things are much worse in the sense that Putin is actually waging war, active war on Ukraine. That's much worse. It's much worse in the sense that I don't dare go to Russia again now. The odds of my being kidnapped and held for ransom are fairly high. That was never the case before. I am a foreign member of the Russian Academy of Sciences. I have various honors from scientific organizations in Russia, but I just can't. It's not safe. On the other hand, in the depths of the Cold War, particularly the earlier parts of the Cold War, you had similar issues of do you collaborate or do you not collaborate? And I advocated a mixed response, that some of us collaborate, and those who feel strongly that they shouldn't, then they take a firm stand on it. So Richard Feynman, a very close friend of mine, refused to go to the Soviet Union and refused to collaborate. I chose to do it, and I think we both respected each other's position, and we both thought that what the other person was doing played an important role. I did believe then, and I still continue to believe that having good communication so that you understand each other is essential for the security of the world. And if you cut off communication, it makes the world much more dangerous. And so I do continue to travel to China, and I would continue to travel to Russia if it were safe. But I also speak out very strongly against what is going on in Russia, against what's going on in the United States with Donald Trump, and against what Xi has been doing in China. So somehow that doesn't prevent me from getting into China, but Russia is completely different. It's really extremely disturbing what's going on with Russia. I do think that if Putin is not stopped in Ukraine, Ukraine is just the beginning, and he'll probably go for the Baltic states next, and well, we'll see.
So maybe a more joyful question now. I write a lot of books, blog posts, and so on about science, trying to pass the feeling I have about the universe because of physics. And yesterday I was at a music concert, and I was envious of the fact how some of the emotions can be transferred, I feel, more easily using music and so on. But you also had huge success in transferring the feelings of awe using Interstellar, helping with a book by Carl Sagan, Contact. So maybe tell us a little more about the importance of transferring the feelings we got from doing physics.
I certainly think that let me approach this in a different way. When I was 4 years old, my grandfather told me that if I got a job when I grew up that was like play, then I would be a success. I didn't fully understand what he was saying until later, when I came to realize that a big part of this was that if you really love what you're doing, you're enthusiastic, you have strong emotions about it, then you're willing to work very, very hard. And working very, very hard is central to success in most things, particularly the difficult things we do as physicists. So that's part of the answer, that and part of what I try to convey to non-scientists is the joy of understanding the world, the joy of discovery. There is a documentary movie that is circulating in film festivals at the moment. I don't think it's been shown fully broadly yet, called Far Away Nearby, by a filmmaker named Paula Froley. And this documentary, the central concept of this documentary is the role of emotion in science. And Paula uses Joseph Weber and his attempt to discover gravitational waves, his belief that he had discovered gravitational waves, the way that the pieces of the scientific community came down on him very hard, criticizing him when it became clear he hadn't seen gravitational waves. And huge amounts of emotion involved in this to explore various aspects of emotion in science. And I think this is a superb film. And it really brings out the importance of emotion in driving us to do science, the importance of emotion in inspiring us, and inspiring a non-scientist about the path that we are choosing to go on. And we will try to take them with us on this path, because after all, they're the source not just of the money that we need for big projects, but also it's their children who become the future scientists. And so emotion, awe, shared with non-scientists is really very important. On the other hand, emotion has to be sharply controlled when you're searching for truth, and as emotionally involved as we may be in wanting to have seen gravitational waves, we have to be absolutely firm with ourselves and with each other in requiring very high level of proof before we make any kind of a claim. And so there are these two sides of this issue of emotion.
So we should probably conclude shortly. So I have two final questions. Maybe you have one, so I'll ask the first one. What does the future hold for you? Next couple of weeks, months, years? You like long projects, so what are you working on right now?
Yeah, so I'm in a phase of my life where I have retired from my professorship. I retired because I wanted to be in control of my own time. No longer have any responsibilities except those that I choose to do in some particular project. So I've been doing projects such as the movie Interstellar and a book of paintings and poetry called The Warp Side of the Universe that I recently published with Leah Halloran. But another project, and the thing that is occupying almost all my time, I think, for the next year, maybe year and a half, is a history of the LIGO project for detecting gravitational waves, which I co-founded with Rayem Weissem and Ronald Drever, and which ultimately had success. And so I conceived this history and I'm leading it. I have a writing team of 6 of us, and that includes one superb editor and me and 4 others who played central roles and of one type or another in making this thing succeed. This project was probably the most technically difficult project that physicists have ever done. It took Rayem Weissem and me 50 years. It took other members of the team 40 or 30 years, but it was a very long-term project. Cost $1 billion US. It took 1,000 people in the collaboration. It was very, very complex. It involved extreme politics in Washington from our funding agency in Congress. It involved huge amounts of different kinds of technology and engineering because there were so many things that go wrong. And it had sociological aspects of it that were difficult, very difficult, and how do you deal with a transition from small science to big science. So at the beginning of the pandemic, I said to myself, I can get the attention of these people who are working so hard on LIGO until the pandemic is over. Let's see if we can do this history. And so we got started, but we're still continuing. It's a history that where I think of it as more than anything a resource for future historians, because we know the project inside out ourselves. We're too close to it to write an objective history. We're doing the best we can. But we also know huge numbers of primary documents, contemporary documents. And our history is tied to enormous numbers, to literally several thousand unpublished contemporary documents. And so those will be made available to future historians. And it's also a history that will be of interest, I think, to a large number of people too, as well. So anyway, I'm in a big push to bring this to completion, because I've been working on it since 2020. And
so you don't want people in 1,000 years wonder about how you managed to detect gravitational waves the same way as we are now wondering how people build pyramids. They didn't write a book after.
Yes, so these are the blueprints for yes. So anyway, I have that. I'm thinking of writing a novel when I get. You
still have some spare time to.
Yeah. Well, this history will be done within 2 years, maximum 2 years, maybe 1 year, and then one of the next things is a novel that I'm thinking of writing, a science fiction novel that involves a lot of science, but different kinds of science than Interstellar. But I'm still writing poetry and doing poetry painting collaboration with Leah Halloran, where we did do a book, but we have more material that we've created, and we're doing live performances at places like Starmus, and having a lot of fun, and I think entertaining and inspiring some people with it.
Do you have a final question?
Oh, I would have so many questions still. I would love to ask you about contact and wormholes, but if I have one final question, something that really interests me these days. So we are discovering the supermassive black holes very early after the Big Bang, like less than 500 million years after the Big Bang, we see that there were black holes that were 10 to the 8 solar masses. What do you think? How did they originate? Is it direct collapse? Is there still a way to grow these black holes so big in such a short time? Or perhaps could there have been primordial, very massive black holes that actually could have grown to those masses very early on? What is your take on this?
I don't have a take, because it's a topic that I have not really dug into deeply. And so I have to ask you what your take is. In general, I try hard not to make statements or opinions about things unless I have put a fair amount of time and effort into trying to understand them. And this is one that I have not. I mean, it's really strange. It's exciting, but
yeah.
You tell me.
Yeah, I just know it's exciting, and yeah.
So I started with an emotional question, or question about how do you feel about the sky. So I'll also conclude with a non-scientific question. I asked my wife, she's basically doing ceramics, so something completely different from science. What would her question for you be? And she asked, if you wish something to happen in the next 10 years, what would that be?
I would like, for me, the most interesting question for the next several decades in areas that I'm close to is the origin of the universe and the laws of quantum gravity that presumably control the origin of the universe. So the thing I would most like to see is primordial gravitational waves that come from the earliest moments of the life of the universe. In the next 10 years, our only hope for that, I think, serious hope, is through those primordial gravitational waves influence on microwaves, electromagnetic microwaves, the so-called cosmic microwave background, on the polarization of the cosmic microwave background. So I would like to see absolutely definitive and clean, and everybody agrees, observations of this imprint that primordial gravitational waves could place on the polarization of these microwaves that come not from the beginning of the universe. These are microwaves that were produced when the universe was a few 100,000 years old, much later. But those imprints would be very valuable if we really see them definitively. It would be a first step, because the next step is to actually directly see primordial gravitational waves, but to see them in a very different frequency band. This imprint that is left on the microwaves, that's left by primordial gravitational waves that today have wavelengths of hundreds of millions of light years. And but we have the possibility with a future space mission, a follow-on after the LISA mission that the European Space Agency is preparing to do, we have the possibility to directly see the primordial gravitational waves with periods of a few seconds to a few minutes. And and having those with this very short period and the things with periods of hundreds of millions of years, having both of those so widely separated in their period of the waves, it could be tremendously powerful, especially if those waves have surprising properties. There is a conventional prediction for what those waves will be. The conventional prediction comes from a hypothesis that all that came off the Big Bang at the beginning was what we call vacuum fluctuations, the least amount of gravitational waves the laws of physics would allow. And then they get amplified by processes in the early universe. I have seen us be very wrong about things that seemed obviously true during my career. And I would like us to be very wrong about the predictions on these primordial gravitational waves. And that I would like to see that trigger a huge breakthrough in our understanding of how the universe was born and the laws of quantum gravity.
I'm nearly sure this isn't the answer she was anticipating, so thank you for it. And thank you for your time.
Yeah, thank you very much.
Thank you.
So you can find us everywhere online, and see you next time.
Very good. Great questions. Nice conversation. Yeah.
Thank you.